Today, our group is going to talk about magnetic properties of materials. So, what is magnetic properties of materials? Let's go! The magnetic behavior of a material is governed by the interaction of the magnetic dipole moments of its atoms with an external magnetic field. The nature of the behavior depends on the crystalline structure of the materials and is used as a basis for classifying materials as diamagnetic, paramagnetic, or ferromagnetic. Now, let's look at the differences between diamagnetic substances, paramagnetic substances, and also ferromagnetic substances. Diamagnetic substances are those substances which are feebly repelled by a magnet. Examples of diamagnetic substances are antimony, bismuth, copper, gold, silver, quartz, and many more. Paramagnetic substances are those substances which are feebly attracted by a magnet. Examples of paramagnetic substances are aluminum, chromium, alkali, and alkaline earth metals. Ferromagnetic substances are those substances which are strongly attracted by a magnet. Examples of ferromagnetic substances are iron, cobalt, nickel, and so on. When a diamagnetic substance is placed in magnetic field, the lines of force tend to avoid the substance, as shown in this figure, where it is being slightly repelled by the magnet. Next, for paramagnetism, the lines of force prefer to pass through the substance rather than air, so it is slightly attracted, as we can see right here. Next, for ferromagnetism, the lines of force tend to crowd into the specimen, so we can see that most of them are strongly attracted by the magnet. As you can see here, all the lines are trying to go into the magnet, then it comes out of the magnet.
Now I would like to introduce about the formula of the magnetic field. First of all, these diagrams represent the wire. So the symbol H is represent magnetic intensity, I is represent current, and N is represent the conducting wire carrying current every unit length. So the magnetic intensity is the product of currents and the number of times the conducting wire carry currents. So this magnetic intensity is formed in the wires and around the wires. So when the magnetizing is crossing through the air, it will be reduced by permittivity by mu naught, means the permittivity of the free space. Therefore, we have B naught equal to mu naught times H. Next, we have a material. So this material will be placed inside the wire. So therefore, this material will be magnetized. So we have the symbol of M, which is represent the magnetization within material. When the magnetizing is exposed outside the material, it will be reduced by a mu naught factor. Therefore, we have Bm's equal to mu naught times M. B is represent the total magnetic field and is sum of the magnetic intensity within the wire and the magnetization within the material. So when we are taking the two equations at the above, this Bm and this B naught, substitute inside this equation, we will get B equal to mu naught H plus mu naught M. When mu naught is factorized, B equal to mu naught times H plus M.
This is an Example of paramagnetic substance and diamagnetic substance. When a paramagnetic substance is placed in a magnetic field like this, the magnetic field lines prefer to pass through the substance like this. Now it shows that the magnetic induction inside the sample is greater than the magnetic induction outside the sample. The magnetic susceptibility of paramagnetic substances has a small positive value. Now let's take a look on diamagnetic substance. This is the magnetic field. Not to south, not to south, not to south. When a diamagnetic substance is placed in the perpendicular direction to the magnetic field, like this, sample, the magnetic field lines prefer to pass away from the substance, like this. Now it shows that the magnetic induction inside the sample is lower than the magnetic induction outside the sample. The magnetic susceptibility of diamagnetic substances has a negative value.
This curve. Hysteresis is actually the characteristic of a ferromagnetic material. Okay, B. B is the magnetic field developed inside the ferromagnetic material, while H is the magnetizing field. So, let's start by assuming a magnetic core is unmagnetized so that B equals to 0. As H is increased from 0, B increases proportionally. When H reaches a certain value, the B begins to level off. As H continues to increase, B reaches a saturation value. So this is called the saturation point. Once saturation point is reached, a further increase in H will not increase B. If H is decreased to 0, B will fall back along a different path to a residual value. This is called the BR value. This indicates the material continues to be magnetized even H is removed. So this is called the retentivity. A reversal of the magnetizing field is represented by the negative values of H on the curve and is achieved by reversing the current in the coil. An increase in H in the negative direction causes saturation to occur. When the H is removed, the flux density goes to the negative residual value. The flux density follows the curve back to its maximum positive value when the H saturation is in positive direction. This is called the complete BH curve.